Unit 7, pages 214 to 215, solving differential equations. Examples of variable, separable differential equations. So solving differential equations, this word solving means that we're finding the equation of which the differential equation is the derivative. Okay, so differential equations are derivatives. We're trying to figure out what equation that derivative is for. Okay, so we've looked at differential equations before when we were actually finding them. Now we're going to actually solve them. So given below are differential equations with given initial condition values. We want to find the particular solution, y equals f of x, for each differential equation that satisfies the given initial condition. So this is asking us for particular solutions. When it's asking for particular solutions, it wants you to solve for C. Okay, so when we get to a point where we have a general solution, I'll point that out. But the particular solution requires you to continue and use that initial condition to solve for C to find your final equation. So let's look at these problems and do them out together. So this first problem, we have dy dx is equal to 6x squared plus 6x plus 2, and f of negative 1 is equal to 2. So first thing that we want to do is separate the differential equation. So we want to separate all the x values on one side, all the y values on the other. So in this situation, our dy is our only y value, so we want to keep that on the left, and we want to move the dx to the other side. So we'll have dy equals 6x squared plus 6x plus 2 times dx. Okay. So now we're in a situation where we have dy and dx on opposite sides. So we can take the indefinite integral of both sides of this equation. So on the left side, we're taking the integral of dy, or in this case, 1 dy. So if we find the antiderivative of 1 in terms of y, that's 1y plus c. And on the right side, the integral of 6x squared plus 6x plus 2 is equal to 6x cubed over 3 plus 6x squared over 2 plus 2x plus c. Okay, so if you look at this problem, we have two c's. C just represents constant, right? So we're going to absorb all the constants into one value of c. So this is going to give us y equals 2x cubed plus 3x squared plus 2x plus c. So all of our c's have been absorbed here. So all constants absorbed into 1c. Because c just represents constant. We don't know what the constant is, it's just represented in one value. Okay, at this step where we have y equals an equation, this is a general solution. Okay, this means that if we did not have an initial condition, we would be done. We cannot solve this any farther. We are as solved as we could be without an initial condition. However, we are given the initial condition, f of negative 1 is equal to 2. So what we're going to do here is we're going to substitute negative 1 in for x and 2 in for y and solve for c. So we'll have 2 equals 2 times negative 1 cubed plus 3 times negative 1 squared plus 2 times negative 1 plus c. So we have 2 is equal to negative 1 plus c. So 3 equals c. So our particular solution, since our initial condition was in f of x form, we're going to write our particular solution in f of x form. So our final equation is f of x is equal to 2x cubed plus 3x squared plus 2x plus 3. So this equation is the antiderivative of our dy dx. Okay, so let's do another problem. Here we have, again, dy being our only y value. We're going to move the dx over to the other side. So we have dy is equal to 1 plus 12x to the 3 halves over 2x to the 1 half dx. Okay, so let's simplify this fraction really quickly so that we can integrate it quickly. So we have dy equal to 1 half x to the negative 1 half plus 6x dx. So now we can integrate both sides of this, and we get y equals 1 half x to the 1 half times 2, or divided by 1 half, plus 6x to the squared divided by 2 plus c. Okay, and if we simplify that, that's y equals square root of x plus 3x squared plus c. And here's our general solution. We have y equals and then a simplified function. Now we're going to apply our initial condition. So 0 is our x, 2 is our y. So 2 equals square root of 0 plus 3 times 0 squared c. So 2 equals c. So our final equation is f of x equals square root of x plus 3x squared plus 2. Okay. For the next two problems, as we solve this, we're going to get to a point where we don't actually need a general solution before plugging in our initial conditions. Okay, so for these problems, we have y in two places, and we have x in two places. So what we're going to do is we're going to move all the y's onto one side, all the x's onto another side, and go from there. So to move 2y to the left, we have to multiply. So we have 2y dy equal to x squared plus 2x dx. All right, now we can integrate both sides. So the antiderivative of 2y in terms of y is 2y squared over 2 plus, equals the antiderivative of x squared plus 2x. So we get x cubed over 3 plus 2x squared over 2 plus c. So we have y squared equals 1/3 x cubed plus x squared plus c. So from here, if we didn't have an initial condition, we could just square root the whole thing and get a general solution. However, we don't need to find a general solution for this. We could just plug in our initial condition of x being 0 and y being 2. So we have 2 squared equals 1/3 0 cubed plus 0 squared plus c. So 4 equals c. So we can plug that in and we get y squared equals 1/3 x cubed plus x squared plus 4. And to find our particular solution, this is where we square root. So we get y equals square root of 1/3 x cubed plus x squared plus 4. And to keep it so that it's in the same terms as our initial condition, that states that f of x is equal to the square root of 1/3 x cubed plus x squared plus 4. Okay, so I want you to try number 4 on your own. Do the best that you can to identify the f of x equation that is represented here. Okay, for number 5, we again are going to separate our y's and our x's. So our y's need to be on the same side, our x's need to be on the same side. So in order to move our y minus 2 over to the left, we have to divide. So we have 1 over y minus 2 dy is equal to x to the 4th dx. We can rewrite this as y minus 2 to the negative 1 dy is equal to x to the 4th dx. So when we take the integral of both sides, we have a function to the negative 1, so that gives us ln. So we have ln of the absolute value of y minus 2 equals x to the 5th over 5 plus c. So in the previous video, I talked a little bit about why when you antiderive a function and it becomes ln, you need to remember to put the absolute value signs. It's because the domain of ln is only positive values. So we can't have y minus 2 being negative or else ln doesn't work. So let's simplify a little bit. So we have ln absolute value of y minus 2 is equal to 1/5 x to the 5th plus c. So this is another problem where we don't need to find the general solution quite yet. We can just start from here, move forward with the initial condition. So both y and x are both 0. So we'll have ln of 0 minus 2 equals 1/5 0 to the 5th power plus c. So we get ln of 2 is equal to c. ln of 2 is a number. It is a number, so it equaling c does make sense. We don't actually have to find what ln of 2 is. We don't need to. It's not necessary, so we're not going to. So what we're going to do now is plug that value in for c. So we have ln y minus 2 equals 1/5 x to the 5th plus ln of 2. Now, a particular solution has to equal f of x. So in order to get there, we have to first have it equal y. So we're going to solve this equation for y. So to get rid of an ln, we need to apply the exponential function e. So we're going to take e to all of this. So we have e to the ln y minus 2 is equal to e to the 1/5 x to the 5th plus ln of 2. Now, properties of exponents tell us that e and ln cancel each other out. So on the left side, we just have the absolute value of y minus 2. And then on the right side, properties of exponents tell us that if our exponent is separated by addition or subtraction, well, if our exponent is separated by addition, it's the same thing as taking e to the 1/5 x to the 5th times e to the ln of 2. So we're going to separate this using properties of exponents. Okay, and then the next step, we again have an e to the ln, which will cancel each other out. So we have absolute value of y minus 2 equal to, cancel it out, so we get 2e to the 1/5 x to the, okay, we're that much closer to solving this now. Now, because this is absolute value, that means that we have two possible equations that we can look at. We can either look at y minus 2 equals 2e to the 1/5 x to the 5th, or y minus 2 equals negative 2e to the 1/5 x to the 5th. We're going to solve for both and just check to make sure they work. Okay, so now when we add 2, we get y equals 2 plus 2e to the 1/5 x to the 5th, or y equals 2 minus 2e to the 1/5 x to the 5th. Now to just double check and make sure they work, our initial condition said that f of 0 equals 0. So if we plug in 0 on the right equation, we get 0 equals 4, which is not the case. So this equation doesn't work because f of 0 does not equal 0. However, in the right equation, if we plug in 0, we get 0 equals 0, which is correct because f of 0 equals 0. So our actual equation or function is f of x equals 2 minus 2e to the 1/5 x to the 5th. Okay, that was a lot, but I do want you to try number 6 on your own, trying to follow the steps that I took to make sure that you get a valid answer.